Hi folks, I'm here with one more episode of the Supply Chain Show, and today I have a very special guest. I have Joannes with me. He's the CEO of Lokad. Lokad make a very interesting software and a product using the most advanced methods of demand forecasting, mathematical modeling. Joannes has a master's in mathematics and also a master's in computer science, so a very unique combination. He's the CEO for the last 12 years. I'm already part of his Lokad TV, because if you want to know about some really advanced topics, especially in inventory management, forecasting, demand forecasting, and supply chain in general, you should visit Lokad TV. I was guest on one of his shows, so that's why we got to know each other. So today I've taken opportunity to bring him, and we will talk about the 6 generations of forecasting. Very interesting concept Joannes has come up. And so without any delay, Joannes, welcome to the show. How are you? Just please tell me about yourself. How's things? How's business these days?
Thank you very much for having me on the show. So business is good, surprisingly so, for Lokad. I'm afraid that for many verticals that we serve, it's very, very tough. Aerospace is absolutely terrible. Fashion is like super, super tough. But well, we are doing our best to help our clients to survive. On the e-commerce is still striving, but I don't think it's going to surprise most of the audience. So indeed, and Lokad. So Lokad is at its core, we are a software vendor, enterprise software vendor, and it's a company I founded 12 years ago. And early on, I realized that, well, if you want to optimize, a supply chain, you need to look ahead, because you can't, 3D print everything on the spot, not yet at least, and you can't teleport, the goods either. So whenever you want to serve a client, you need to somehow, anticipate a bit the need if you want to be able to serve the clients. Thus, one way or another, you end up doing some kind of a forecast, no matter how you look at the problem. And so we started our journey, and indeed we have been doing through 6 generations. I do not claim that there is anything, fundamental about those generations. They were mostly accidental development of the journey of Lokad. And it went like this. The first generation was the classical time series, forecasting techniques. I was fresh out of university, started a PhD, never completed it. And lo and behold, let's do, time series forecast. There was a few twists to have a bit more accuracy, but fundamentally it was very much aligned with the idea of time series forecast, by day, by week, by month, the super classic stuff nowadays. And what was the problem? Well, the problem was we were actually winning benchmark after benchmark accuracy-wise, and yet when we were deploying the damn thing to our clients, it was actually usually making things worse, although the forecast was more accurate. So it was very, very puzzling to me. And then I realized that it took me quite a few years, I'm making the story brief, that actually something that should have been obvious to me from the start is that supply chain costs are concentrated on the extremes. It's not the average that matter. It's the statistical extreme. It's the extremely high demand that causes the stock out, the extremely low demand that creates the dead inventory, dead stock. In between, where the inventory rotates just fine, there is no much problem. And thus, the problem is that the classic forecast, generation 1, was focusing on what happens in the middle. This is the wrong place to focus. It's the extreme. And that led us to the first generation, which are the second generation, quantile forecasting. We want to forecast the extremes, and thus we add bias on purpose. And it took me years to come to that, because it was so bizarre. Whenever you're talking to forecasters, usually they say, oh, we want to remove bias. Why would you like to have a forecast that has bias? Would you do that even on purpose to add even more bias on top of the bias? And the short answer of the second generation of our forecast engine was, yes, actually, yes, we do. We want a massive bias toward profit. That's kind of weird, but that's a long story short. And then you realize that you have plenty of problems that requires all sorts of various degrees of biases. So it's not just you want to have like the extremely high scenario, you want to have the extremely low scenarios, and maybe a lot of halfway through scenarios as well. And so that brings me to the third generation, which was Quantile Grids. It was pretty much more of the same, but instead of having like one extreme scenario, you have maybe like 20 different scenarios. And then we realized that so that was this generation of quantile grids. So we were adding, more and more quantiles. So it was forecasts, but all sorts of biases. And then we realized that the problem, it was not just the demand we wanted to forecast. It was also lead times. It was also returns. It was plenty of other areas where there is uncertainty. The areas that we want to forecast is not just demand. It's literally there is at least a dozen of distinct problems where you need to look ahead. There is uncertainty. There is patterns. For example, lead times. There is a Chinese New Year that happen every year. So basically, factories in China close. So the lead times get longer. It's very predictable. So lead times has some degree of randomness to it, but there is also plenty of things that you can predict, and you can even apply statistical methods to it. Thus, long story short, we went to the fourth generation, which was our first probabilistic forecasting engine. And that was, first, there was two areas where we were departing from the quantile grids. First, we wanted to look at all possible futures with probabilities, not just a series of quantile steps. So it was mathematically quite different in terms of way to organize the algorithms and the inner working of the engine. It was quite different. And then we were starting to embrace the idea that we would be looking at a lot of different type of forecasts, not just demand, lead times, returns, etc., etc. And then that was the fifth generation, was basically deep learning. Deep learning is something that came. It was a different type of a breakthrough. It was suddenly we realized that tackling a large set of different things, forecasting demand, forecasting returns, forecasting lead times, forecasting price variability, forecasting quality defects, forecasting tons of things. We realized that there was a problem of expressiveness. So you want to have machine learning, statistical learning in high-dimensional spaces. That's what modern machine learning is about. And you realize that you need to have something that is very, very versatile. And it turns out that basically this is pretty much, among many other things, what deep learning brought to the scene. And by the way, deep learning was profoundly different compared to all the methods that were before. Before deep learning, machine learning, libraries were set of models. Let's say, for example, gradient boosted trees. You have a method you apply. You have a package algorithm to do that, and so far until basically 2014 or something, machine learning was mostly a vast collection of models, and Lokad was internally like that. A collection of models. Deep learning suddenly, it was programmatic. The evolution emerged with TensorFlows. It was suddenly like a sub-programming language of its own, which is kind of very bizarre for a machine learning technique. And we used that, and it turned out that most of those elements were actually geared for problems that were completely unlike supply chain. It was geared toward problems like image recognition, voice synthesis, image synthesis. Very interesting problems, but fundamentally problems that are also very, very different from supply chain problems. And so when we took deep learning, which was basically I would say an all-the-board improvement compared to what we had before in terms of expressiveness and kind of accuracy, although with probabilistic forecast accuracy is relatively tricky, we realized that there was a lot of accidental complexity at the software level. So those toolkits contain tons of stuff that were very useful for image analysis, but not so much for supply chain optimization, predictive supply chain optimization. And when we removed all the accidental stuff that is not super relevant for supply chain, what is left is something that has actually a name. It's called differentiable programming. You could see that as either a descendant of deep learning or a subset of deep learning, depending on the way you look at the problem. And I did not invent the term. That was smart folks at Facebook that invented the terms. And if I have to basically describe why it's so game-changing, this late stage, it's because it lets you embrace supply chain data, which is usually very relational in nature, because the data is obtained through ERP, MRP, WMS, e-commerce platforms, etc., where the data does not present itself as images or time series. It presents itself as relational databases. And the interesting thing is that you have like high-dimensional methods that can literally embrace the very structure of the problems, both the structure in the sense of the structure of the supply chain problem, but also in a very mundane way, the structure of the data that you're working with, which just happen to be relational data. And that was, so that was, in long story short, a journey where Lokad went through. And nowadays, I would say most of what we are doing it with differentiable programming. It's still probabilistic forecast, and it's still very much supply chain driven, but we added this sort of tag, those sort of tags to all those generations to make them slightly more comprehensible.
No, I think great answer. I think of how you explain. So I've got the question on the last two actually. So my understanding is deep learning is essentially the part of the whole machine learning as a body of knowledge, right?
Yes.
So why deep learning was not good enough, and you have to take to the next level of differentiable programming? I mean, what is the actual technical difference?
Yes. So the emphasis of deep learning is, as the name suggests, deep networks. So networks that have many, many layers. And the idea is that you want to be able to build extraordinarily complex functions to capture extraordinarily complex phenomena. And that's very interesting if you want to do image analysis. You know, images are incredibly rich. And if you have a function, you know, a mathematical object that is too simplistic, you cannot capture anything. And it's only possible to do that because you have enormous, you have data sets that are absolutely gigantic. So you have literally billions of samples. So you have an object that is very, very complex, but also you have a near infinite amount of data available to train your model. That's, I would say, the key emphasis of deep learning. You want to be able to learn arbitrary complex functions using arbitrary large data sets. And that works very, very well in areas where functions are very complex and data is very, very much abundant. So now if we go to the supply chain world, first, are functions very, very complex? To some extent, yes. To some extent, yes. But you have a problem when you learn a super complex function, what you end up with is also a super opaque model. So that's a very, I would say, very, that's a problem that turns out to be very operational, is that when you have to deal with a statistical model that is completely opaque, that creates a whole series of problems when it comes to putting that in production in a real supply chain where you're going to have daily decisions about millions of euros or dollars of production. And you really want to have a high degree of transparency, not just for supply chain practitioners, but also for what we call at Lokad supply chain scientists who operate the models. Because one of I would say, the dirty secret of deep learning is that the models are very opaque, even to the data scientists themselves. So that's I would say, a very dumb problem. So you want to kind of make it much more transparent, even if you have to somehow renounce to the capabilities of the model. So a slightly less capable model, but a lot more transparent. That's one thing. And the second thing is, do you benefit from near infinite data sets? In supply chains, absolutely not. Usually data is very, very scarce. And so your focus is not so much that you can learn a lot from a near infinite data set. The challenge is that you want to learn a lot from a data set that is, on the contrary, very, very limited. So what matters is not scalability of your model. What matters is known as data efficiency. And that brings me to another thing that may sound like super bizarre, is the modern way to have a very, very high degree of data efficiency, so you can learn a lot from the data, is to inject what is known as structural priors about your data set. So just to give you an idea about the sort of mindset that goes into this, we can safely assume that if we do a promotion, the impact will only be positive in terms of uplift for the products. Yes, in theory, the impact in terms of sales volume could be both positive or negative. That would be theory. In practice, we can assume reasonably, because we have our experience, we understand how the world works, we would say if there is a promotion, the impact has to be positive. If it's negative, the model is not sensical. This is not doing anything that is making any sense with regard to the fact that it's an article that has been promoted. Thus, if you restrict the statistical model from learning, the situation where the impact would seemingly seem negatives, you can actually learn more from the data, because from a statistical perspective, your model doesn't have to learn as much. You've kind of structured the problem. Also, just to give you another example that is even maybe stronger, cannibalization in fashion, for example, cannot happen with sizes of very, very distinct, very, very different sizes. So maybe you will have cannibalization between shoes that have, very close sizes, but if you have like shoes that are 5 sizes apart, there is no cannibalization whatsoever if you're speaking of the same client. So you see, and again, you can try to learn that from the data, from scratch, or you can kind of inject some kind of priors. This is very different from, I would say, the sort of knowledge injection that was done in the 60s with the expert system. The expert system was saying we are going to go all the way and literally embed the rule in the system. And there is nothing left to learn. A modern approach is we want to kind of frame what we want to learn, and then let something like differentiable programming operate within something that is slightly more constrained, so that you don't learn from with no assumption whatsoever. You're kind of slightly constrained, and that lets you, I would say, operate with a much greater data efficiency. And that's what differentiable programming is about, to be able to inject this kind of small dose of structural common sense, if you want.
No, that's fine. I think I want to go back to the point you make initially, which is about the quality of the data, right? So the quality of data in generally supply chain is not good. So then you mentioned about the scalability of the software itself, and I think, this is one of the problems I've seen, and I've seen some really good supply chain software. Again, they use the same terms as machine learning, AI, etc. But the data quality is not good enough for the ML algorithms to learn from it, and that's one part. And the frequency of data sometimes is not good enough. Maybe in e-commerce industry where there's a lot of orders are processing, but if you go to real traditional manufacturing where you process your weekly orders and your monthly orders, the data frequency is just not there for the algorithm to learn and make and suggest smarter decisions. So what do you think about that? Expand on this more based on the clients you work with.
So I do acknowledge the fact that there are tons of data problems. However, my understanding about the root causes is very, very different. Very, very different. And it might be a surprise to your audience. When people say bad data, my understanding is profoundly different. And I would say in the Western world, among developed countries, for the last 2 decades, most supply chains have been digitalized. And the quality of data, objectively speaking, is excellent, in the sense that companies knows exactly what they buy. It's in the system with a great accuracy. So we have not even, 1% of clerical error in terms of data entries. They know exactly what they produce, they know exactly what they have in stock, and they know exactly what they sell. So as far those fundamental data are concerned, for the last 2 decades in Europe, in North America, I'm not saying necessarily in Africa, but in I would say rich countries, this data has been excellent for at least 2 decades. But people still have a lot of problems, and I will get to the 2 root causes. One is first, when most of the competitors of Lokad are having problems, it's because they have basically prepackaged enterprise software that includes machine learnings, and those prepackaged products makes very strong assumptions about the way the data should be. And then you have what I call a massive impedance mismatch between the way the data is in, let's say, the MRP, and the way the data is expected to be from the size of the enterprise software vendor that is supposed to do anything smart with the data, planning, production optimization, or whatnot. So that's the first root cause, is literally that you have something that is a massive impedance mismatch where the assumptions, the core assumptions, just don't match. And then there is no way to reconcile, because fundamentally your MRP has its own design, which is usually, it's a reasonable design. I'm not saying it's a bad design, it's just the way it is. It's fairly reasonable. The enterprise software has its own design. It's just the way it is. It's reasonable in its own way. But the two put together just conflict, and they don't match. So that's the first source of problems, impedance mismatch. The way Lokad we have approached this solution is to entirely give up on the idea of having a pre-packaged enterprise software product. We have, that's where differentiable programming really shines. It's programmatic. So you can literally embrace the way the data present itself in the ERP or MRP or WMS or whatever, instead of trying to make the data fit your own system. So you see that we completely reverse the thing. So that's my first criticism. And suddenly when you do it like this, you realize that most of those supposed data problems just go away. So that's the first point. The second point is when you say it's too infrequent, is I believe that there has been like a very strong misguided approach to statistics in supply chains, where people mostly look at models that extensively relies on the law of large numbers. And that's exactly what, when I was telling you about this data efficiency thing, when people say it's too infrequent, my own, when the data is too infrequent, I say, yeah, it's perfectly true that you have only one batch a month, maybe in many industries. And this is not a criticism. This is just the way the world is. So it's not, it's just fact. And so the question is that do you have statistical tools that are geared toward very limited data, very sparse data, or do you have tools that are geared, statistically speaking, that are geared toward massively available data? And by the way, that was the distinction that I made between deep learning and differentiable programming. It was we had to engineer things that would embrace the fact that supply chain data are very sparse nearly all the time. Even if you look at the supposedly highly rotating situation, like in a store, 90% of the time, if you look at a SKU on any given day, the sale is just zero. You see, most SKUs are not even sold once per week in any store, even in an hypermarket. In an hypermarket, half of the stores are sold less, half of the SKUs are sold less than 1 unit per week. So, so data is always very scarce. And thus, you need to have something that is going to really do the most of the data that you have, and hence the need for data efficiency. And that brings me to the second problem about data problems, is that you need to remove the impedance mismatch, and you need to embrace something that makes the most of the data as you have with very high data efficiency. And that's really where differentiable programming really shines on both fronts.
No, I think that's interesting. I want to go back to the point you made on the most of the ERP software they have the predefined assumption, and that is one of my pain point. I mean, the logic of MRP was developed in 1956. The grid is established, is available. Unfortunately, it hasn't really changed and is still used in most of the books, right? But this is what I hate. Let me use the word, because I wrote a blog on why ERP sucks, and one of my criticism is they are not open, they are not scalable, they are not integrated. They are not agile enough to fit into the business model, because the business model of any business changes every 2 years. I mean, the business model pre-COVID, post-model, or post-COVID for most businesses is different, but the software assumption is not changing. But I think you briefly touched on Lokad have adopted a different approach to that. So expand on this a bit more, how you have catered that problem, which is not working around the predefined assumption. So I'd like to learn a bit more on that.
So I think ERP is a misnomer. It should have been named, it was a name conjured by some market research firm in the late 90s, and actually it's a deep misnomer. It should have been ERM, Enterprise Resource Management. So the whole point is just to keep track of the assets. Nothing less, nothing more. And the same is for MRP, which should have been, Material Resource Management. And this is it. So the crux of the problem is that people expect more from the software, but I believe that it's a misguided expectation. So the first thing is that if we say that the software should only be doing that, just keep track of the assets, the products that we have right now are doing a decent job. It's not necessarily, super good. And if I have to do one criticism, is that with the age of the internet, most of the super tight integration that was necessary until the late 90s is no more. So you see, until the late 90s, it was an absolute nightmare to design a piece of software that was distributed, where you would, basically have this, two pieces of software that would, work collaboratively in two distinct machines. So you had to bring everything back together into the same mainframe, otherwise the thing would never work. With the rise of internet, basically, it becomes increasingly easy to build what is known as distributed software. And suddenly, it means that from an engineering perspective, a software engineering perspective, you can apply a divide and conquer strategy where you can split your IT landscape into many smaller apps that are much more manageable. So you see, so my main criticism with ERM, ERP, it's you don't need something that is monolithic anymore. Then in terms of asset management, I think it's decent. Where it's never going to be great is that if you want to do anything, any sort of things that involve data crunching of any kind, then your main obstacle is the relational database itself. If you look at data mining, machine learning competition like 𝐥𝐤. 𝐥𝐤 is a platform for literally machine learning competitions. You will see that out of the thousands of competitions that took place on 𝐥𝐤, people have never won any competition using a SQL database. And there is a very good reason. A SQL database grants you integrity. It gives you atomicity, transactionality. It's absolutely not designed to do anything that is related to statistical analysis. So, and literally, there are very good reasons. I cannot go into the detail, but the idea that you can use a relational database to do anything that would be akin to a statistical analysis is a bit ludicrous if you want to do anything that is not just like an average, So, bottom line, it's the wrong tool. So don't blame a vendor for not being able to deliver anything built on top of a relational database that is supposed to be any kind of smart analytics. There is fundamental limitations in the base layer. But again, I'm not saying that those relational databases are bad. They give you transactional integrity. It's very important. It means that, for example, if you buy something from a supplier and there is a payment to be made, you really want, and that the software crashed right in the middle of the process, you cannot end up with a relational database. You will not end up with a situation where you've already paid the supplier, but you do not record that you've already paid the supplier, so you trigger the payment a second time after you recover from the crash. So your transactional software prevents some classes of mistakes that were exceedingly expensive in the early, I would say, in the early 70s. So that's something that is very, very good. And now, so Lokad, we position ourselves as if we entirely give up on the idea of managing anything. So Lokad doesn't manage anything. We don't keep track of anything. All of the data is managed by the ERM, if you want. If we say that we free ourselves entirely from all the burden of tracking those assets, so we only deal with data that is kind of dead, past, it's just the data as it happened. We don't care about what is happening right now in terms of real time. Suddenly, you realize that you can do a lot more on the analytics side, and that there are plenty of things that are way easier to engineer and way simpler to do. And that's so that, the way Lokad was built was mostly to think about building, a platform for predictive optimization of supply chain with a programming twist in mind. And again, scalability. As soon as you basically give up on the idea of having transactionality in your system, suddenly it's way easier to be like super scalable. For example, in Lokad, one of the key design decisions was to do everything in batch. So everything in batch means that we want to have the results fast, like in a minute, but not in a millisecond. Because there is something that might be very profoundly unintuitive, is that if you want to have like a software that is like real time, so that it can answer your questions in a few milliseconds, it may be very counterintuitive, but usually the software is dramatically inefficient in the way it's going to use its processing power to answer your question. So if you can have like a batch design, it means that instead of trying to answer one question in a millisecond, you're going to answer 1 billion questions in a minute. You see, that's the game being played. So Lokad, we think of, instead of thinking how can we do a smart analysis on one SKU in a millisecond, we think, can we have a complete system-wide, looking at the entire supply chain analysis that is very smart, looking at 10 years worth of data, except that we don't do it real time, we do it in a minute. But it's not real time, and we can do it in batch. And we can extensively leverage the fact that having a batch architecture is give us a massive degree of flexibility when it comes to do smart calculation at scale.
No, sure. So that leads to the few end questions I have. I think you said on your website that despite all the smart technology, statistical skills, all the good words you've used, and you claim that there is for the users there is a zero statistical skills required, right? So can you explain that part?
So first, again, the problem is when you claim that people should know about statistics, I would say which kind of statistics? It's an enormous body of knowledge, and the bulk of this body of knowledge is not even remotely relevant to supply chain problems that we have. And same could be said for like 99% of the machine learning techniques that have been developed over the last 7 decades. So first, I would say first, we need to think of something where we find, the things that are truly relevant and that really embrace the sort of constraints that we face in supply chain. For example, where the problem of learning from the data and delivering some kind of numerical optimization are usually completely entangled. So first, if what you find in the literature is only very distantly relevant, we say it's a waste of time. Just fast forward and get to Lokad and start learning things that are, at least in our eyes, have some are at least I would say truly relevant from a production perspective. Then the second thing is the way we have engineered the technology, and I believe that goes to the success of Excel, is that my belief is that if you have technologies that are too technical, you end up with all the sort of problems that makes literally all the data science initiatives fail. I've seen data science initiatives fail over and over and over. And why is that? Because when you have a knowledge that is so arcane, it's so complicated, that basically you end up in a situation where either people are data scientists and they know a lot about those super fancy models, or they are supply chain expert, and you can't have both because it's kind of above human. So maybe once in 1,000 you will find somebody who is both a supply chain expert and a data scientist and a software engineer and a chess master and a football player and whatever. But it's like 1 in a million, and usually it's very hard to be a supply chain expert. It's very hard to be a data scientist. It's very, very hard to be a decent software engineer. So the problem is if you expect to have too many competencies, reality is that people are very crappy at all those things. So we have engineered a technology, a technology that is programmatic. So, and by the way, Excel is programmatic. You can write formulas, where we have paid an enormous amount of effort to make it accessible to people who are supply chain experts. So where, yes, there are statistical capabilities, but they have to be made simple enough so that with just a few weeks of training can be made accessible to people who are who are supply chain experts and who will remain supply chain experts. And by the way, that was one of the reasons why Lokad a decade ago started to hire. We went from hiring data scientists to supply chain scientists, and we started to hire just people that were just engineers, with the idea that we should be able to train them technically on our platform, Lokad, in just a few weeks. And just to give you an idea, when we welcome a junior apprentice supply chain scientist, learning about Lokad is mostly the technicalities. It takes about a month. To become a supply chain expert, I estimate it takes about 2 years. So you see, basically learning about all the depth of knowledge about all the supply chain expertise is literally an order of magnitude more difficult than learning about the technicalities about Lokad as a tech platform. And it boils down to the fact that how did we do that? Well, we did just like what is done in Excel, is we want to have something that is programmatic, but also there are plenty of things that in terms of complexities that we don't need. For example, object-oriented programming is very interesting, but it has literally zero use whatsoever if you want to optimize a supply chain. So Python is great, but Python, suddenly you have to know all about plenty of things about object-oriented programming, although it's never going to be of any use for any of the problem that you're about to be solving in supply chain. So why should you take a tool that puts as a tax tons of knowledge about object-oriented programming, although you're never going to use it? And for example, another example, if you want to do data crunching on a large data set with Python, it turned out that Python natively is quite slow. So if you want to be fast, you need to use specialized libraries for hardware acceleration, like NumPy. Why should you, as a supply chain practitioners, know anything about hardware acceleration to basically do scalable computation? If I look at Excel, for example, Excel done by Microsoft, if you have a large calculation, automatically your spreadsheet is going to use multiple CPUs on your machine to speed up the calculation. Excel will not ask you to use a special library or to use the Excel spreadsheet in a specific way to leverage multiple CPUs. Excel just does that for you natively. But with Python, you have to learn a lot about hardware acceleration in order to take advantage of that your machine has multiple CPUs. And that's it's a complete accidental complexity. So you see, my point is programmatic capabilities doesn't have to be super complicated, but we have to pay a lot of attention so that the supply chain scientists, supply chain engineers, are not, overwhelmed by technical details that are almost completely irrelevant to the task at hand. And that's exactly has been the focus of Lokad. Can we do something that is that is as easy to operate as Excel, except that is completely geared towards supply chain problems? And that was literally what we did.
No, that's great. I've got a few minutes. Just last question with I think you do offer inventory optimization as a service. So how does it work? That means companies send you data, you do the work and send them back. Is this literally as simple or more complicated?
Yeah. It pretty much sums it up. The thing that is very atypical is that when we say they send data, we send results. It's not a system that sends a result. It's a supply chain scientist at Lokad who take ownership of the entire numerical recipe. So that means that whenever we suggest, for example, to purchase 1 unit of material, it's not a system that says, please purchase that. It's literally a supply chain scientist that says, I'm taking ownership on the fact that this is the correct suggestion for your company. And if we want to debate that, I'm very up to debate on why in dollars I believe that is literally the most profitable thing that you should buy right now. The next unit you should buy, if there was only 1 unit of anything that you could buy at the present time, this should be this 1 unit. And we have this super hands-on approach where we literally take ownership so that we don't fall to, I would say, the problem that most of our competitors suffer where nobody bears the blame. The system keeps producing crap, and basically people are going to blame data, people are going to blame whatever, the pandemic or whatever. The approach that we have at Lokad, we believe that we have a very strong technology, but we never hide behind the technology. The idea is whenever we take on a case, it's ultimately a supply chain scientist. The client knows the person. This supply chain scientist know the company quite intimately. Usually they even go on site, visit the facilities, try to really understand how things operate. And then when there is something that goes wrong, it's not about being super tough on the person, but somebody has to be accountable. So there is to be true ownership so that it's not wishful thinking when it comes to the improvements. Because if nobody is responsible, when there is a big screw up, how are you going to improve? So you need to have somebody who take ownership of the good and also of the bad so that you can actually improve. And and I know that it's a very tough job for those supply chain scientists at Lokad, because it's a lot of pressure. Some of them are managing, above, €1 million worth of inventory. So that's enormous responsibility that they bear on their shoulder. But nevertheless, they can also take a real pride in doing their job very, very well. And from the perspective of the client, it gives them something that is also, you can certainly have a very intelligent discussion about the numerical recipes. Because again, Lokad, there is no technology to do the forecast. It's a numerical recipe crafted thanks to the programmatic stack of Lokad, but ultimately, the numerical recipe is literally what is crafted by the supply chain scientist. It's up to debate, and we can debate on whether the approximations that are being made are correct or incorrect, whether the strategical thinking that went into this numerical recipe is aligned with the actual strategy of the company or not, etc. And that pretty much sums up the sort of relationship that we have with our clients.
Thank you very much, Jonas. I think it's a very heavy discussion. I think it's not for the faint-hearted, for sure. But definitely, I really enjoyed it, learned a lot, and thank you very much for the time, for the viewers. If you like this conversation, if you like me to do more of the same, interview people, send your comments, send your topic, and we'll find people, and we can do more content or different content if you like. So have a good day. Take care of yourself. Good night.
Thank you very much, and wish the best for the SCMDOJO. You're doing a great work. Thank you very much for having us.
So if you like this video, don't forget to like, share, subscribe, and leave your comments below.